In today's video lecture, we are going to continue to talk about transient RLC circuits. We'll start by going over the algorithm for source-free RLC circuits with no source present after t equals 0. In other words, we're assuming that we have an RLC circuit being energized by voltage or current sources up to time 0. At time 0, whatever sources are present are removed, so that all that's left is the capacitor, the inductor, and one or more resistors. And we're going to see that the energy that is stored in the capacitor and the inductor is going to get dissipated through the resistors, and will end up having the response eventually decay to 0. So here's the algorithm. We're going to see that a lot of the steps are very similar to what we saw in the first order case, with some minor wrinkles. So the first step is just like in the first order case, we have a steady state problem. The only difference is now we're finding both IL of 0 minus and VC of 0 minus because we have both an inductor and a capacitor present. And as in the first order case, right after the change in the circuit at t equals 0, the voltage across the capacitor and the current through the inductor are unchanged. The other thing we need to do, just like in the first order case, is if the variable that we're ultimately looking for is something other than VC or IL, find its value before the discontinuity as well. Note that x of 0 plus does not necessarily have to equal x of 0 minus. It depends on what the variable x is. The next step is you redraw the circuit after the change, and then if necessary you simplify it so that you get either a capacitor, inductor, and a series resistor, or capacitor, inductor, and parallel resistor. Once you have a simplified circuit, you find the differential equation model for whatever you're looking for, whether it's VC or IL. Alternately, and this is key, we're going to see this in examples, we can just use the canonical results that we determined previously. We know from here that if it's a series circuit, that becomes a differential equation, and if it's a parallel circuit, that becomes a differential equation. The next step is you find the characteristic polynomial and you get the form of VC or IL. And once again, the form is going to take on one of three variations. If your roots are real and distinct, we're going to get the first case, which is overdamped. If the roots are real and the same, we get critically damped. And if the roots are complex conjugates of each other, we get this underdamped situation. Notice in each of these, we're going to have two unknowns, either A1, A2, B1, B2, or D1 and D2. So step 4 and 5 are related to finding those A1, A2, B1, B2, and D1 and D2. And this is where it gets more complicated compared to the first order case. So in the first order case, there was only one unknown, and there was one initial condition. Now we have two unknowns and two initial conditions. The problem is the initial conditions are not in the form that are useful for finding the unknowns. So this is what we need to do. Once you have the form of the solution, you want to differentiate that equation to get another equation. So if you had VC, you get VC prime. If you had IL, you get IL prime. What you want to do now is come up with a new initial condition. So the initial conditions that you have, are VC of 0 plus and IL of 0 plus. The initial conditions that you want are VC of 0 plus and VC prime of 0 plus, or IL of 0 plus and IL prime of 0 plus. So what step 5 does then is it takes the initial conditions you have, that one, and you manipulate them to get the initial conditions you want. and this is best illustrated with examples, so we'll do this in the coming pages. Step 6 now, you have two equations, VC and VC prime, or IL and IL prime, and you have two initial conditions. These new initial conditions, you have VC and VC prime, or IL and IL prime at 0 plus. You plug those initial conditions into your equations that you have from step 3 and step 4. So in step 3 and step 4, you have two equations. In the initial step and step 5, you have two initial conditions. You plug those initial conditions into the equations to solve for A1, A2, B1 and B2, or D1 and D2. The final step, which is one of these steps that you don't necessarily have, is if what you're looking for is something other than VC or IL, you find a general expression relating that variable to the variable that you solved for in step 6. And as in the first order case, this step may or may not be necessary. So this algorithm on the surface looks much more complicated than the first order case, and it is more complicated. The simple fact that you have three cases, underdamped, overdamped, and critically damped, makes it more complicated. The fact that you have two initial conditions and two unknowns, the A1 and A2, B1 and B2, D1 and D2, makes it more complicated than the first order case. But to be quite honest, the only step that is really difficult, in my opinion, is step 5. So let's go through and do some examples, and hopefully that'll clarify this algorithm. Okay, so in this problem, we're given an RLC circuit that's initially driven by a 12-volt source, and at time 0, the source turns off. So if you think about what the source looks like, Vs of t starts off at 12 volts, and at time 0, it turns off. So let's go through the algorithm. The first thing we do is a DC steady state problem before the change in the circuit at t equals 0. So at 0 minus, we have a 12-volt source, a resistor there. Remember, an inductor in DC steady state is a short circuit, and a capacitor in DC steady state is an open circuit. So we have that. VC of 0 minus is pretty simple. Because the capacitor is in parallel with the inductor and the inductor is a DC short, the voltage across the capacitor has to be 0 volts. And of course, it's also the voltage across the capacitor right after the change in the circuit. The current through the inductor, we can use Ohm's law. The 12-volt source is going to make current be produced. That current can either go through the inductor, the capacitor, or the resistor. It's all going to go down through the inductor. And so that current is just 12 volts divided by 6 ohms, or 2 amps. So these are our initial conditions. For now, we're just going to set them aside. You now redraw the circuit. After the change. The voltage source now shuts off. The inductor is no longer a DC short. The capacitor is no longer a DC open circuit. So we get that. The next thing you do is you manipulate the circuit as needed to get it into a single series or parallel RLC circuit. Notice the 3 ohm and 6 ohm resistors are in parallel. They become a 2 ohm resistor. Then we have our inductor and our capacitor. The next thing we need to do is find the differential equation associated with this circuit. Turns out that any voltage and any current in this circuit has the same form of the differential equation. So we can basically solve for whatever we want. Now in this case, we're ultimately looking for VC anyway, so we might as well solve for VC. And we're going to start by labeling those currents as follows. And let's do a KCL. We know that IL plus IR plus IC is equal to 0. But the current through an inductor is 1 over the inductor value times the integral of the voltage across the inductor. But of course the voltage across the inductor is the same as the voltage across the capacitor, so we can write it as that. The current through the resistor is VR over the resistor value, but VR is the same as VC, so we can just write it as VC over 2. And of course the current through a capacitor is the capacitor value times the derivative of the voltage across the capacitor. From here, we can take the derivative of that whole expression and divide by this term here, and we get the second derivative of the voltage plus 5 times the first derivative of the voltage plus 4 times the voltage is equal to 0. This becomes our differential equation. We actually did not have to go through all of these steps here. If you look back to our summary, for a parallel RLC circuit, we know that the differential equation has to be this form. So you can use these canonical results if you want, but it's nice to remember where those results ultimately came from. They came from things like KVL and KCL equations. From here, we now get the characteristic polynomial. It's going to be s squared plus 5 times s plus 4 is equal to 0. And once again, it's worth noting, this 4 is nothing more than 1 over LC. This 5 is nothing more than 1 over RC. So once we had this expression here, we could go directly to the characteristic polynomial if we wanted to. I just did these steps above to show where that comes from. We now find the roots of this. The roots are minus 5 plus or minus the square root of 5 squared minus 4 times 4 all over 2. That becomes minus 5 plus or minus 3 over 2 minus 4 and minus 1. Right away we see that this is the overdamped case. So we know the form of VC and IL, in fact for any voltage and current, has to be the sum of two decaying exponentials. Since we are looking for VC, that's what we will solve for. So VC of t is going to be some constant, A1 times e to the minus 4t plus A2 times e to the minus 1t. To solve for A1 and A2, we not only need two initial conditions, but we need two equations. We get a second equation by taking the derivative of this expression here. VC prime of t is the derivative of that. It's going to be minus 4 A1 e to the minus 4t minus a2 e to the minus t. To solve for a1 and a2, we need two initial conditions. We need VC of 0 plus, and we need VC prime of 0 plus. VC of 0 plus we have already. It's 0 volts. Determine that there. The second initial condition is at step 5 in the algorithm. This is the hardest part of the second order RLC problems. And it's really not that hard, but it is, in my opinion, the hardest part. So to get VC prime of 0 plus, we need to think about some things. We know that C VC prime of t is IC. The current through the capacitor is the derivative of the voltage across the capacitor times the capacitance. But what is IC of t? IC of t plus IL plus IR is equal to 0, so IC equals minus IL minus IR. So IC of t equals minus IL of t minus IR of t. And IR of t is nothing more than VR of t over R, and VR is the same as VC. So that means that VC prime of t is 1 over C times minus IL of t minus VC of t over R. We can now plug in t equals 0 plus to get VC prime of 0 plus to be 1 over C times minus IL of 0 plus minus VC of 0 plus over R. At this point, we know that VC of 0 plus is 0 volts. We know that IL of 0 plus is 2 amps, once again, from the previous page. We know the capacitor value is 0.1 farad, and so we know that the second initial condition is now minus 20. We can now plug in that initial condition plus the original initial condition of VC of 0 plus to solve for A1 and A2. So VC of 0 plus, which is 0 volts, is going to be A1 times e to the 0 plus A2 times e to the 0. So from that we get that A1 plus A2 is equal to 0. From the second of the new initial conditions, we get VC prime of 0 plus is minus 20, and that equals, plugging into that equation there, minus 4A1 e to the 0 minus A2 e to the 0. So from this one we get minus 4A1 minus A2 is equal to minus 20. Two equations and two unknowns, we can solve for them and we get that A1 is 20/3 and A2 is minus 20/3. So we get that the voltage across the capacitor is 0 volts for t less than 0, and it's going to be 20/3 e to the minus 4t minus 20/3 e to the minus t volts for t greater than or equal to 0. Let's plot this. So we know that VC of t is 20/3 e to the minus 4t minus 20/3 e to the minus t. What this is the sum of two decaying exponentials. Let's draw those separately. So 20/3 e to the minus 4t, this one has a time constant of 0.25 seconds. It's going to start at 20/3, and it's going to decay to 0, and it's going to take 1.25 seconds to get there. So this is what 20/3 e to the minus 4t looks like. Minus 20/3 e to the minus t has a time constant of 1 second. So it's going to take 5 seconds to decay to 0, and it's going to start at minus 20/3. And it's going to decay this way. And it's going to, once again, take about 5 seconds to get to 0. The total response is the sum of these two. So if we look at it, we notice that at time 0, we're going to start at 0 because 1 starts at minus 20/3 and 1 starts at 20/3. Well, we notice then, because the second term decays more slowly than the first one, that number is going to be greater than that number. So now the response is going to go down. It's going to become negative. But eventually, it's going to go to 0. So the response is going to look something like this. It's going to start decaying, but eventually it's going to stop and go to 0. So once again, early on, this is much more negative than that is positive, but as we continue on, the difference eventually gets to 0. So this begs the question, at what point does this response turn around and start heading back up to 0? Well, to do that, we need to take the derivative of Vc of t again and set it equal to 0. So to find the turnaround point, take the derivative of that. Vc prime of t is now going to be minus 80/3 e to the minus 4t plus 20/3 e to the minus t. We set that equal to 0. You get that e to the minus 4t equals 1/4 e to the minus t. If you then take the natural log of both sides, remember the natural log of e to the x is just x. So the natural log of e to the minus 4t is just minus 4t. Minus 4t is the natural log of 1/4 e to the minus t. The next thing you should remember is that the natural log of a times b is the natural log of a plus the natural log of b. So the natural log of 1/4 e to the minus t is the natural log of 1/4 plus the natural log of e to the minus t, which is minus t. So you get that minus 3t is the natural log of 1/4. Solve for t, you get t equals 0.462 seconds. And to find the value at that, you just plug that into the original equation. Vc of 0.462 is going to be what? 20/3 e to the minus 4 times that minus 20/3 e to the minus 1 times that. And you work that out, it ends up being minus 3.15 volts. So we get that, and we get that. Now, this problem did not explicitly ask us to find this. I just added that as additional information. But what we see in a second-order RLC circuit that is overdamped, your two responses that are going to be added together are each one going to be a decaying exponential with different time constants. And then when you add them together, in this case, we get something that goes down, becomes negative, and then it eventually decays to 0. Depending upon what these coefficients here were, you could have a situation where it doesn't peak first, that it starts at a maximum value and decays to 0 steadily as a single decay rather than as something that goes in one direction then turns around. It really depends upon the initial conditions. The other point to make is that how long it takes for the response to decay to 0 is going to depend on the two individual time constants. Notice the individual time constants were 0.25 seconds and 1 second. This is the longer of the two, so it's going to be the dominant time constant. So it's going to take 5 seconds to decay to 0. Let's do another example. It's actually the same circuit. The only difference is our inductor value is different. So the only change is a value of L. So that's going to change the characteristic polynomial, which is going to change the roots, which is going to change the form of the solution. Notice that our initial conditions, because our initial conditions themselves did not depend on the value of L, our initial conditions are not changing. So in this example, because the initial conditions did not depend on the value of L, so they're unchanged. So a lot of the steps we don't need to do. We know that IL of 0 plus is still 2 amps. We know that VC of 0 plus is still 0 volts. And we still know that VC prime of 0 plus, this third initial condition that we found, is still minus 20. I should point out that sometimes if you change a single circuit component, you do need to recalculate the initial conditions. In this example, we did not. Okay, but what did change is the characteristic polynomial. Because the characteristic polynomial does have L in it. Remember, it's S squared plus 1 over RCS, so that doesn't change, plus 1 over LC. That does change. So because we changed L, this term changes. So now the roots are going to be minus 5 plus or minus the square root of 5 squared minus 4 times 62.5 all over 2. Now we get complex conjugate roots. We're going to get minus 5 halves plus or minus J 15 halves. This is going to be an underdamped case. Remember, in an underdamped RLC circuits, the real part of the root dictates the decay, and the imaginary part of the roots dictates the frequency of oscillation. What we're going to end up with is a decaying sinusoid. So we know we're going to get a situation that looks like that, where the frequency is dictated by the imaginary part, and how quickly the decay happens is dictated by the real part. So we know that VC of t is going to be e to the minus 5 halves t times d1 cosine 15 halves t plus d2 sine of 15 halves t. To find d1 and d2, we need two initial conditions, which are unchanged from before, and we need two equations. So the second equation we need is VC prime of t. Here, you have to think back to Math 140. The derivative of this expression is the first times the derivative of the second. The derivative of a cosine is a minus sign, and you bring out the frequency, so it's minus 15 halves d1 sine 15 halves t. The derivative of a sine is a cosine, no minus. So it's first times the derivative of the second, plus the second times the derivative of the first. This looks a little complicated, but fortunately, when we plug in t equals 0, a lot of things go to 0 or 1. So let's do that now. We know that Vc of 0 plus was 0 volts, and that's going to be e to the 0 times d1 cosine of 0 plus d2 sine of 0. Cosine of 0 was 1, sine of 0 is 0, e to the 0 was 1. We end up getting that d1 is equal to 0. Likewise, Vc prime of 0 plus, which we know has to be minus 20, has to equal this long expression here evaluated at t equals 0. We get e to the 0 times minus 15 halves d1 sine of 0 plus 15 halves d2 cosine of 0 plus d1 cosine of 0 plus d2 sine of 0 times minus 5 halves e to the 0. E to the 0 is 1, sine of 0 is 0, cosine of 0 is 1, cosine of 0 is 1, sine of 0 is 0, and e to the 0 is 1. You get a lot of things simplifying, and you end up getting that minus 20 equals 15 halves d2. So we can now put this together. We saw from the previous page that minus 20 is 15 halves d2, so d2 is minus 40 over 15. We can now plug that in to get Vc of t is going to be 0 volts before the circuit changes, and it's going to be minus 40 15ths e to the minus 5 halves t times sine of 15 halves t volts for t greater than or equal to 0. This response has two parts. You can think about this as our exponential decay envelope. And then here's our sinusoidal part. So let's think about the decay envelope. It's going to have a magnitude of 40 over 15, so not quite 3. It's going to decay to 0 with a time constant of 2/5 of a second. So the time constant is 2/5 of a second. So it's going to take 2 seconds to go to 0. So it's going to look something like that. And we'll put the decay envelope at both positive and negative sides. Now inside here, we want to put the sinusoid. So let's think about the frequency of oscillation. So the frequency of oscillation is 15 halves radians per second. So the period is always 2 pi over the frequency of oscillation, which is 4 pi over 15, which is approximately 1 second. So it's going to take about 1 second to oscillate. The last thing we see is that because of this minus sign, it's a minus sign, it's going to start at 0, and it's going to become negative before it becomes positive. So it's going to become negative with a period of about 1 second. So it's going to go negative till it hits that envelope, goes positive, then it hits that envelope. It's going to look something like that. So once again, the envelope of the decay depends on that part, which in turn depends on the real part of the root, and the frequency of oscillation comes from that part, which ultimately depends on the imaginary part of the root. So we see that both the real and imaginary part of the roots of the characteristic polynomial, which themselves come from the values of R, L, and C, dictate the general shape of the response, and then the amplitude comes from the initial conditions. Let's do a third example. So it's a slightly different circuit, and in this one we're asked to determine R so that the circuit is critically damped. So now we have an unknown component, and we're not asked to solve for any voltage or current in the circuit. We're asked to simply find the value of R to make it critically damped. So we don't have to worry about initial conditions here. All we need to worry about is a characteristic polynomial. So if you think about it, for t greater than or equal to 0, we're going to have a single resistor, which is going to be the 6 ohm resistor in parallel with R. So we have 6 in parallel with R. That in turn is going to be in parallel with our 2.5 Henry inductor and our 0.1 farad capacitor. So we know that our characteristic polynomial, once again, this is a parallel RLC case, so it's S squared plus 1 over R equivalent times C times S plus 1 over LC is equal to 0. For critical damping, you want this coefficient squared to equal 4 times that one. So you want 1 over R equivalent C squared to equal 4 over LC. That's how you get critical damping. So if you solve for R equivalent squared is going to be LC over 4C squared, or L over 4C. We know the value of L. We know the value of C. You get 6.25. So R equivalent is the square root of that. It's 2.5. Units is ohms. Finally, that's R equivalent, not R. So R equivalent is 6 in parallel with R, and that's going to be the product over the sum, and that has to equal 2.5 ohms. You solve for R, you get R has to be 15 over 3.5 ohms. Now, this problem did not ask us to find the solution or even the form of the solution, but let me just sketch a couple things. We know that the characteristic polynomial, in this case, is going to be S squared plus 1 over R equivalent times C times S, which is 4S, plus 1 over LC, that's 4, set it equal to 0. Sure enough, if you find the roots of this, you get minus 4 plus or minus the square root of 4 squared minus 4 times 4 over 2. You get the repeated roots, and so you know that VC of t or IL of t, or any other voltage or current for that matter in the circuit, has to be B1 times e to the minus 2t plus B2t times e to the minus 2t. And to continue with this problem, if we wanted to solve it completely, you would then need to find what B1 and B2 are, and those would depend upon your initial conditions. But this problem did not ask for that, so we will not worry about that. Let's talk a little bit about driven RLC circuits. So driven circuits in second order is just like driven circuits in first order. There's still an abrupt change in the circuit at T0, usually 0, but now we're going to have a source present after 0. What this means as far as the differential equation goes is we're still going to have a second order differential equation, but now the right-hand side is not going to be 0. What this means is the total solution is going to consist of both a homogeneous solution like we had before. So this is what we had in the source-free case, but now we're also going to have a particular solution which is of the same form as whatever this forcing function is. In this class, the forcing function is going to be a constant, and so that term is going to be a constant. So when it's all said and done, we know that the particular solution, or the forced response, is just going to be a constant. We'll call it x of infinity. All that this means as far as our equation goes is we have this additional term that shows up in each of the overdamped, critically damped, and underdamped cases. And that value comes from a DC steady state problem as t goes to infinity. So let's briefly look at the algorithm again, and we're going to see that it only adds a couple steps. So the first step is the same. You find your initial conditions. Second step is a new step. After the discontinuity, you find a new steady state value of either VC or IL, depending upon what you're ultimately looking for. Step 3 is the same. You basically find the form of the solution. And once again, we will almost always try to use canonical results. You find the characteristic polynomial, find the roots of the polynomial, you find the form underdamped, overdamped, critically damped. The one difference is here in step 4. When we get to the general form, do not forget to add this term here. It is important to add that term before you solve for your A's, your B's, or your D's. So you add the final value before you solve for your coefficients. The next couple steps are identical to before. To solve for A1, A2, or B1, B2, or C1, C2, we need to differentiate whatever we have in 4 to get a second equation. Then we find a new initial condition. Remember, just like before, the initial conditions we had were VC of 0 plus and IL of 0 plus. What we want are VC of 0 plus and VC prime of 0 plus. So you need to manipulate your initial conditions to get them in the new form. I should point out here that depending upon what we're looking for, rather than VC here, we may want IL. Anyway, once we have our new initial conditions, we can solve for A1, A2, B1, B2, or D1, D2 by plugging the initial conditions that we have from step 6 into our equations in steps 4 and 5. Finally, in step 8, if what we're ultimately looking for is something other than VC or IL, we need to find a general expression for that variable in terms of VC and IL, and then solve for it that way. Bottom line, in the driven case, there are only a couple minor differences. First off, in addition to doing a DC steady state problem at 0, you need to do a DC steady state problem at infinity. Second step that's different is step 4. We need to add this term before we solve for our coefficients. And other than that, all the steps are the same. So in our next lecture, we will do some examples with this general solution algorithm. Have a good day.